calculus, we're going to be looking at implicit differentiation today, which I am sure is my favorite thing all semester. So we're going to look first of all at this circle, which is something we haven't looked at before. So if I have x squared plus y squared equals 25. I have a circle of radius 5, just to get an idea of what we're talking about here. Forgive my bad drawings, please. Okay, so an ellipsis circle, 5, and so on. So we've got our old skills we could put into play here. If we wanted to find dy dx, we could write this expression as a function of x, and we would have the positive or negative square root of 25 subtract x squared. So we would have the upper functional arm and the lower functional arm, which is how we would approach it in grade 11. So we could rewrite this, for some of us it's just helpful if we write that as 25 subtract x squared to the 1/2. If we want to find dy dx or y prime, we would, don't forget we have the upper and lower functional arm, so that our derivative will also have two pieces. Bring down the 1/2, 25 subtract x squared to the negative 1/2. Don't forget the guts, and there it is. Not impossible, but quite ugly. And that was a fairly simple circle. So if we have other equations that are uglier than that, our derivatives could get ugly fast. So there is a better way. If I want to find dy dx of x squared plus y squared equals 25, instead of writing it as a function with two pieces, I can take the derivative the way it is. So my big idea is that I'm going to take the derivative of both sides, which means I'm going to take the derivative of every term. So here we are. Here's our Leibniz notation. I'm going to take the derivative of the first piece with respect to the letter x. I'm going to take the derivative of the second piece with respect to x. And I'm going to take the derivative of the other side also with respect to x. So I've done the same thing to both sides. It's just a little bit weird with the second term. So for the first term, we know how to take the derivative, of x squared. It's simply 2x. Yay! I know how to take the derivative of the right side. The derivative of any constant is 0. It's that weird piece in the middle. I'm taking the derivative of y squared, but not with respect to y. So how do we do that? We use the chain rule. So I'm taking the derivative of the function. Don't forget the guts. The guts is dy dx. So this essentially is the guts. A way to remember it is the letter doesn't match. So I have to take the derivative of that letter with respect to x. Okay, I'm going to simplify now. I want to know what dy dx is. That was my purpose. So I'm just going to dy dx. I'm going to subtract 2x from both sides. And I'm going to divide both sides by 2y. My dy dx or y prime is negative x over y. Well, that's just a little bit strange. Let's look at our diagram again. If our derivative is negative x over y, so dy dx. Let's look at some specific points. So right here, for instance, let's use red. There we go. Right here, for instance, my tangent slope should be undefined, straight up in the air. My x value is 5 at that point, and my y value is 0. 5 over 0 does give us an undefined slope. Makes sense. Let's look at another place that I know right here. Badly drawn, but my x value is 0, and my y value is negative 5. 0 over negative 5 as a slope there is 0, and that's what I'm seeing on my diagram. Let's look at a second example. Find the slope of the tangent to the ellipse x squared plus 4y squared equals 25 at the point -3, 2. The first thing I would like to do is just draw a rough diagram. Ellipses are not in the curriculum so much anymore. So a strategy we can employ is to come up with the intercepts if we want to draw it. So for my x-intercepts, when my y value is 0, I have +5 and -5. Okay. For my y-intercept, when x is y-intercepts, when my x value is 0, I have y squared equals 25 over 4, which is positive and -5 over 2. Okay, so that gives me a sense of what this thing looks like. There we go. All right, we have our function. We want to find the slope of the tangent. So what I'm looking for is dy dx, and I'm looking for it at a specific point. So x squared plus 4y squared is 25. I am going to take the derivative of both sides. So I'm going to take the derivative of each term. The derivative of the second term with respect to x as well, and the derivative of the right side. Okay, so taking the derivative of the left side, my first term is the derivative of x squared with respect to x, super easy. The second term is the derivative of 4y squared with respect to x, which the letters don't match. So the derivative of 4y squared is 8y. Then the guts would be dy dx equals 0. So dy dx, I'm going to subtract 2x from both sides and then divide both sides by 8y. So my derivative is -x over 4y. Does that make sense on what we're seeing? Let's look at a specific point. Let's look at these nice convenient ones. But if you have x is 5, y is 0 at that point, we would have an undefined slope. And at this point right here, when our x value is 0 and our y value is -2.5, I have positive 0 over whatever that is, 10. So I have a 0 slope. Yeah, at least it's looking like it works. Let's find the slope of the tangent at the point -3, 2. So -3, 4 times 2 would be 3 over 8. At the point -3, 2, let's have a look at my really bad diagram. So -3, 2, about right there, and it says the slope of the tangent is positive 3/8. It is certainly reasonable as we look at our diagram. We have another ellipse. This one is much more complicated. I'm going to draw a rough sketch. I had created some points for, but you could look at it on Desmos. It has two x and y intercepts of 1.8 and -1.8, both counts. And then it has interesting values of 2, 2, -2, -2. And it goes a little lower. Wow, that's bad. But anyways, it's supposed to be even. That's the idea behind that one. So it would be nasty to write as in function notation. So we are going to do dy dx by taking implicit differentiation of deriving both sides with respect to x. So here we go. For the left side, we're taking the derivative of the first term. We are going to take the derivative of the second term with respect to x. And lastly, the derivative of the last term and the derivative of the right side, which is going to be 0. Okay, do the easy one first. The first term, the derivative of 5x squared with respect to x is 10x. Yay. The second term is a product. It's negative 6x times y. So with a product, we end up with the derivative of the first times the second plus the first derivative of the second. So we've got that product rule coming into play. We need to be careful. So the derivative of the first is negative 6, and then the second is y, plus the first times the derivative of the second. Well, the derivative of y with respect to x is dy dx. Okay, the last one. I'm going to run out of room. The last one. I'm taking the, plus. The derivative of 5y squared with respect to x is 10y. Don't forget the guts because the letters don't match. Dy dx equals 0. Okay, so now I've got to kind of collect this mess and get dy dx by itself. So I'm going to subtract 10x from both sides and add 6y and get rid of those pieces. And then I have negative 6x dy dx and 10y dy dx. I have a greatest common factor of dy dx, so to speak, but I've got negative 6x plus 10y both times dy dx. And then I'm going to divide both sides by negative 6x plus 10y. So my derivative with respect to x is this expression with x's and y's, just like the last one. But it can get us to the slope of the tangent at certain points. I'm just going to divide everything by 2. It's not a big deal. So that is our derivative, and we've been asked to find the slope of the tangent at 1, negative 1. So my derivative, the slope of the tangent would be negative 5, negative 3, negative 3, negative 5. Negative 8 over negative 8 is a slope of 1 at that place. Let's look 1, negative 1 at my disastrous drawing. 1, negative 1. So it doesn't even go through 1, negative 1. So we'll just pretend it does. And the slope of the tangent is a slope of 1 at that place. It's possible. The last piece of this question is that we were going to find 2 points on the ellipse where the tangent is horizontal. And so, again, horrible diagram aside, we are looking for 2 places where we have a horizontal tangent. I would submit to you they'd be about right there and there. So when I want a horizontal tangent, it's when dy dx is 0. So this is a good challenging problem. We want to know, when is this true? All right, if I multiply both sides by the denominator, I'm really looking for, when is 3y subtract 5x equal 0? I am looking for, when is 3y equivalent to 5x? Or y is 5/3 x. Well, that could be a lot of different places, but I want to know, when does that happen on the ellipse? So I am going to substitute y equals 5/3 x into the original equation. And that will tell me on the ellipse where that happens. So I've got 5x squared subtract 6x times y and 5y squared. So I'm just going to do that. 25x squared over 9. equals 16. So it's messy, but that should find us the places where you have a horizontal tangent, which can be helpful in graphing things. Okay, 5x squared. Subtract 30 over 3x squared. Cool. And then we have ugly. 125x squared over 9 equals 16. Let's collect them all with a common denominator of 9. So I have 45. Take away 90. That's negative 45. Plus 125 is 80. X squared over 9 is 16. To tidy that up a little bit, I have multiply by 9, divide by 80. All right. When x is the positive or negative square root of the right side, or 4 root 5, whichever you like. Those are the two places where the slope of the tangent is 0. I just did a little bit of math for you. The 2 points are 3 root 5, root 5, negative 3 over root 5, comma negative root 5. The arithmetic on that is not the big idea. It's that we have practiced implicit differentiation and can translate a little bit of that information.